All of you welcome. We continue the previous theorem, previous proposition. The given proposition can be proved by showing g of 1 equal to 0. We have defined g of t in the last period. That is to show that g of 0 equal to 0 and g is a constant. From equation 3, we have g of 0. We put in equation 3 0, therefore g of 0 equal to 0 twice pi phi of h0 ds. Now put the value of this phi of h0. We get integration from 0 twice pi f of z into the power is divided by into the power I z minus z minus f of z into ds. Therefore integration 0 twice pi f of z into the power is ds divided by into the power is minus z minus integration 0 twice pi f of z ds. This we separate these two integrations. F of z taken outside the integration sign. Here also f of z taken outside. We take the integration of ds, that is s, and limits from 0 to twice pi. Upper limit twice pi, lower limit 0. 2 pi minus 0 we have twice pi into f of z. Then the value of this integration is twice pi. Therefore g of 0 equal to f of z into twice pi minus twice pi into f of z. We get the value is 0. Therefore we obtain g of 0 equal to 0, equation number 5. So I will write yes into the power is into the power is minus z. Then to show that g is a constant, from equation 4 we write g of t equal to 0 twice pi phi of st ds. Differentiating this equation by Leibniz rule under the integration sign. Therefore we have g dash of t equal to integration 0 twice pi phi dash of st dt. We differentiate under the integration sign. Integration 0 twice pi, derivative of this phi of st, we have phi dash of st ds. From equation 2, phi of st equal to, we get this f of z plus t into e to the power is minus z divided by e to the power is minus z into e to the power is minus f of z. The value of f of z is 0. Now differentiating this equation, we have this derivative of this f function, f dash of this into derivative of internal function, derivative of z plus t into this with respect to t, derivative of z is 0 and derivative of the second term with respect to t, derivative of t is 0, we get this bracket, therefore this bracket into 1. Again multiplied by derivative of internal function, therefore derivative of internal function we have this multiplied by this, therefore this term cancel. Let phi of s2 equal to is e to the power is into f dash of z plus t into e to the power is minus z. Equation number 7. From equation C, g dash of t is given by this. Integration equation 7, taking the integration of this, integration of phi 2 of s3 dt equal to integration of right hand side ds. Now integration of this is given by this e to the power is into f of this function divided by this, here e to the power is cancels and 1 upon I, we get minus I and take t in the numerator, t to the power minus 1 into f of that function. Is the primitive of phi of st, is the integration of phi 2 of st. Let phi of s is given by this, we denote this by phi of s. Equation 8 implies g dash of t equal to phi of s integration limits from 0 to twice pi, therefore upper limit s equal to twice pi, upper limit s equal to 0, lower limit phi of twice pi minus phi of 0, which is equal to 0. Then at the end, since g dash is continuous, we have g dash is 0 and G must be constant. This we have to prove lastly. We have to show that G is a constant. Since G dash is continuous, we have G dash equal to 0 and G must be constant, and G must be constant, which proves the proposition. Hence, the proposition is proved. Next one is the lemma. Let gamma be a rectifiable curve C and Fn and F are continuous functions on the curve gamma. If f equal to u minus limit of fn on gamma, then we have to prove that integration of f over the curve gamma equal to limit of integration of fn over the curve gamma. This is the proof of the lemma. Let epsilon is positive, that is greater than 0, then there is an integer, then there exists an integer n such that mod of fn of w minus f of w is less than epsilon divided by v of gamma. It is for every w on gamma. For every w on gamma, and n is greater than or equal to n. Then we consider the mode of the integration. then mod of integration of f over gamma minus integration of fn over gamma equal to write mod integration over gamma f minus fn. Therefore, we have less than or equal to integration over gamma mod of f minus f of w minus fn of w into mod of dw. Therefore, less than or equal to integration over gamma. We put the value of this from equation 1. We put the value of this mod, that is epsilon divided by mu of gamma, same by equation 1, into mod of dw, same by 1. Now this is constant taken outside the integration sign. When we have integration of this mod of dw, which is nothing but v gamma epsilon divided by v gamma into v gamma. Value of this integration is v gamma. V gamma cancel, therefore less than or equal to epsilon whenever n is greater than or equal to n. Now we have this mod is less than or equal to epsilon, therefore we have integration of f equal to limit of integration of fn, which is the required result that we want to prove. This result, integration of f along gamma equal to limit of integration of fn along gamma. Therefore, the result is proved. Stop here.